Not all particle detectors assembled at CERN are located 100 meters below the ground. In fact, one of them is currently 400 kilometers above the surface of the Earth. In May 2011, the Space Shuttle Endeavour took off for the very last time.
4, 3, 2, 0, and liftoff for the final launch of Endeavour, expanding our knowledge while expanding our lives in space.
It was carrying to orbit a very special particle detector in its payload bay, headed for the International Space Station, the Alpha Magnetic Spectrometer, or AMS for short. Today, we're going to dive into the heart of the AMS detector, which is, at its core, a giant ring of permanent magnets. We'll look deep into the structure of matter to understand how the magnets of the AMS detector work and how they help us answer some of the biggest questions about our universe. So far in these electromagnetic adventures, we've said that magnetic fields can bend the trajectory of electrically charged particles. We've also said that magnetic fields are caused by moving electric charges and by electric currents in conductors. By the way, if you haven't watched those two videos, please start with them. But what does that mean for permanent magnets then? How do they generate a magnetic field? Do they also have electric currents constantly swirling inside them? Today, we've come to the end of this mini-series and we can finally tackle the question of permanent magnets. We'll start this video by introducing a better way to talk about magnets. Then we'll look at magnetism at its smallest scale. Then we'll learn that magnetism comes in more flavors than you might imagine. And we will discover two of its lesser well-known forms before we finally understand how permanent magnets work. Let's do this. We've been talking a lot about magnets in this mini-series, and yet we have not taken the time to be properly introduced to your typical bar magnet, like this one. You might have seen one like this before. They're also known as dipole magnets. What is the first fact that comes into your mind when you think of a bar magnet? Probably that it has two poles, a north pole and a south pole. Here, they're shown in red and green. Maybe you also know that like poles repel and unlike poles attract. And you might also know that if you break the magnet in two, you create two new magnets, each with their own north and south poles. That's all true, but it is a bit misleading. Yes, all permanent magnets have two magnetic poles, but you shouldn't think that the two poles are made of matter with different physical properties. The ends of a magnet are not special or different from the rest of the magnet in any way. Here's a long magnet made of smaller magnets. You see that it can pick up paper clips very well. Let's put the smaller magnets that were at the ends in the middle. Well, the long magnet looks exactly the same and works exactly the same. Another way to say this is that there is no such thing as a magnetic charge. We don't have north magnetic charges at one end of the magnet and south magnetic charges at the other end. And actually, this is one of the fundamental differences between magnetic and electric fields. Electric charges do exist. There are objects around us that have two electric poles. We call them electric dipoles. For instance, let's look at the simple water molecule. That is actually a good example of an electric dipole. The atoms in the molecule bond with each other by combining some of their electrons into pairs. But some atoms are a bit more selfish than others. In the water molecule, oxygen and hydrogen share electrons. But oxygen tends to keep them around itself more often than hydrogen does. It's like two people playing with a ball, but one person holding on to it much more than the other. Since electrons are negatively charged and hang out more often on this side of the molecule than on the other side, you get a side that appears more negatively charged and a side that appears more positively charged. And there you have it. That's an electric dipole where the two poles are made of matter with different physical properties. But that's not how magnetic dipoles work. Poles are not a great way to characterize permanent magnets. Instead, let's say that a permanent magnet is a material having a magnetic moment. That's how physicists say that permanent magnets are made of a material with a magnetic direction, a bit like wood is made of fibers all aligned in the same direction. Now, that's a very specific use of the word moment and has nothing to do with a moment in time. We're not saying that magnets are having a moment, as in they're super popular right now and everyone wants to be friends with them. Although, if you ask me, I would love to be friends with a magnet. I think they're very attractive. So, we represent this magnetic moment with an arrow. The magnetic moment of the bar magnet is what gives rise to its magnetic field, which is shaped a little bit like a donut. A loop of wire with an electric current generates a very similar magnetic field, and so we can say it is magnetically equivalent to a bar magnet. So, we have a better way to talk about magnets. In this chapter, we saw that the poles of a permanent magnet are not special. There are no north charges at one end and south charges at the other end. Rather, we think of permanent magnets as made of a material having a magnetic direction, known as their magnetic moment. Okay, that's all very helpful, but that does not really tell us why a permanent magnet has a magnetic moment to begin with. To understand what's going on at our scale with a magnet, we're first going to have to look at magnetism at its smallest scale. You're probably familiar with some of the fundamental properties of elementary particles, like their mass or their electric charge. Well, particles can also have a magnetic moment. We call it the intrinsic magnetic moment. It's a defining feature of each particle that does not depend on the particle's environment. Let's focus on the electron. Its intrinsic magnetic moment happens to be much greater than those of all the other particles. Basically, an electron itself is magnetically equivalent to a tiny bar magnet. In the materials around us, electrons don't spend their life on their own. They're usually bound to nuclei as part of atoms. So the next stop in our quest to understand magnets has to be at the scale of atoms. Our best scientific model of an atom, or, if you like, our most current understanding of how an atom works is a bit complex. It tells us that electrons in an atom do not behave like little balls. Rather, we describe them as kind of spread out in a region of space around a nucleus all at once. For instance, it becomes impossible to tell where the electron is, what its velocity is, or even if it has a trajectory at all. To really understand this model, we would need to use advanced mathematics, and that's a bit too ambitious for this video. So instead, we're going to rely on a simpler model. Since it's less sophisticated, this other model does not account as well for all the properties of the atom, but it actually does a pretty great job when it comes to its magnetic properties. In this simplistic model, electrons are described as particles orbiting at high speeds around the nucleus along circular trajectories. In the first video in the series, we said that any electrically charged particle in motion creates a magnetic field. In a way, an electron orbiting in a circle is not that different from a loop of wire with an electric current in it. So basically, this situation is magnetically equivalent to a bar magnet as well. We can characterize it with its own magnetic moment, which we call the orbital magnetic moment. So, deep down, there are two reasons why magnets are a thing. Because of the fundamental properties of electrons, and because of the motion of electrons around a nucleus. But almost everything we interact with is made of atoms with electrons in them. So why don't we experience magnetic effects all the time? If it were that simple, why isn't everything a magnet? Well, in most materials around us, those two effects cancel out or average out. And that can happen at three intermediate scales: the scale of the atom, the scale of a group of atoms, or the scale of a group of groups of atoms. We're going to tackle each of these scales in the next 3 chapters. In this chapter, we saw that the reason why magnets have a magnetic moment is twofold. Electrons themselves are particles with a magnetic moment, and they're also electrically charged particles in motion. But those effects cancel out or average out at intermediate scales, which is why most materials don't retain a magnetic moment at our scale. Around us, most atoms don't exist on their own. They tend to bond together to form molecules or crystals, which also means there's basically always more than one electron around. And when multiple electrons have to be roommates in a molecule or in a metal, it gets a bit more complicated. In the real world, most atoms are crowded and don't have a net magnetic moment. Here's why. First, electrons always try to pair up. So a shared home between electrons is less like the dorms at university, where everyone lives their lives independently, and more like a house shared between multiple couples. In a pair of electrons, the intrinsic magnetic moments of each electron always point in opposite directions. As a result, their intrinsic magnetic moments cancel out. Since an electron is magnetically equivalent to a bar magnet, let's experiment with bar magnets. With one bar magnet, you get a magnetic field. But with a pair of bar magnets pointing in opposite directions, the magnetic moments balance each other out, and there is no net magnetic field. Second, electrons always try to orbit in all possible directions. So, in our simplistic model, even though one electron going around a nucleus is equivalent to a tiny bar magnet, many orbiting electrons are equivalent to many bar magnets randomly oriented. So there's no reason why the atom would have a net orbital magnetic moment in any particular direction. We say that the orbital magnetic moments all average out. Those are the two reasons why most materials around us are not magnetic. But to be exact, we shouldn't say that they're not magnetic, because that would imply that these materials never respond in any way to external magnetic fields. And that's not true. Let's pick a material which has seemingly nothing to do with magnetism. Wood. Here's a stick of wood on a little boat floating on the water. If we push the stick, the boat will move however small the force on the stick is. So we can see the effects of even the tiniest of forces. Let's make sure the boat is very still, and let's bring a very strong magnet next to the stick. If we slowly move the magnet towards the stick, the boat floats away from the magnet. Let's do it again from the other side, and this time we speed up the footage. It looks like wood is repelled by magnets. It's not spectacular, but it is kind of mind-blowing. We just witnessed a phenomenon known as diamagnetism, the property of matter to be weakly repelled by external magnetic fields. And there's nothing special about having chosen wood. And there's no such thing as a non-magnetic material. But there is such a thing as a material whose only magnetic response is diamagnetism. Those are said to be diamagnetic. So, what's going on in this experiment? Let's go back to our simple atomic model with orbiting electrons. Well, when we bring in the permanent magnet closer to the wood, the orbits of the electrons around the nucleus tend to align so that all the orbital magnetic moments oppose the external field. In this configuration, we basically have electrons all moving in a loop in the same way, and that is an electric current. And that electric current creates a magnetic field of its own, which opposes the external field. Now, doesn't that sound familiar? It should if you watched the previous video in this mini-series. This is basically electromagnetic induction and Lenz's law, but at the scale of the atom. A changing magnetic field induces an electric current which creates an opposing magnetic field. One key difference between induction in an electrical conductor, like we saw in the previous video, and this new microscopic type of induction is that there's nothing resisting the motion of the electrons from within the atom. Any electron set in motion will stay in motion, even if the external magnetic field stops changing. So diamagnetism will persist, even if the external magnet stops moving. And that's how one gets diamagnetic levitation. Here are a few permanent magnets. If we delicately place this very lightweight and very diamagnetic plate on top of them, a magnetic moment will be induced in the plate in the vertical direction, creating a magnetic field opposing the one from the magnets. The repelling force due to those two magnetic fields pointing in opposite directions becomes as strong as the gravitational force on the plate, so it can stay suspended in mid-air. In 1997, a team of physicists in the Netherlands became quite famous for levitating all sorts of random objects with an electromagnet. They were able to levitate a strawberry, a tomato, even a small frog and a grasshopper. All of these are mostly made of water, which is a diamagnetic substance. And I don't know about you, but I've never been able to levitate a strawberry with a magnet. So what's the catch here? Well, diamagnetism is a very weak effect. So weak that you either need very delicate little experiments, like we did in our two demos, or extremely strong magnetic fields, like those scientists in the Netherlands used. Their electromagnet produced a magnetic field twice as strong as the one from an LHC dipole magnet. So, if we recap what we saw in this chapter, we learned that most atoms don't have a net magnetic moment because their magnetic moments of their electrons cancel out and average out. If an external magnetic field is applied to a group of such atoms, it induces a very weak repelling field in response. That's diamagnetism. Of course, that's not all there is to magnetism, and we still haven't explained magnets yet. It turns out that some chemical elements around us do have a net magnetic moment. They're more difficult to find than those we discussed in the previous chapter. Sometimes, not all electrons in an atom form pairs, and the intrinsic magnetic moment of this one unpaired electron permanently stands out at the scale of the atom, giving it an atomic magnetic moment. The reason why an electron that is part of an atom or a molecule would rather spend its life on its own rather than in a pair is quite complex and requires a thorough understanding of quantum physics. So that sounds like a much better starting point to build a magnet. Let's look at what happens at a slightly larger scale, the scale of a small group of atoms. And, once again, most materials made of atoms that have a magnetic moment do not have a magnetic moment themselves. And that's because most of these atoms ignore their neighbors. You could say they have an independent mind. They couldn't care less about what the neighboring atoms are doing. So in the group, all the atomic magnetic moments point in random directions and keep changing orientation all the time. So really, there's no reason why the group of atoms should have a net magnetic moment in a particular direction. They all average out to nothing, unless we apply an external magnetic field to the material. In this case, the group of atoms behaves like a grid of tiny bar magnets. The atomic magnetic moments all rotate until they're aligned in the direction of the external field. And now we have it, the magnetic moments sort of add up. It's not a perfect alignment, it's a bit disordered, they're wiggling around a bit. The group of atoms has a net magnetic moment, but it's rather weak. In turn, that magnetic moment produces a weak magnetic field which points alongside the external magnetic field. And two magnetic fields pointing in the same direction lead to an attractive magnetic force. That's called paramagnetism. It's the property of certain materials to be weakly attracted by external magnetic fields. Let's have a look at paramagnetism in action. Aluminium is actually one of the most famous paramagnetic materials. So let's put a stick of aluminium on a boat, like we did with the wood, and let's see how it fares when exposed to our giant magnet. This time, we see that the aluminium stick is weakly attracted to the magnet. That is paramagnetism. And also, let's be clear that this attraction is not due to induction, like in the experiments with the coil and the magnet from the last video. The magnet is barely moving. So we're not really creating any eddy currents in the aluminium stick. Another paramagnetic material is, perhaps even more surprisingly so, oxygen. Let's do a demo to convince you. We'll use two liquefied gases, liquid oxygen and liquid nitrogen. Those are gases that have been cooled down to almost minus 200 degrees Celsius. At that temperature, they stop being a gas and condense into liquids. And when we pour those liquids on a table, something really cool happens, literally. We see droplets sliding super quickly. Basically, they're so cold that the table feels super hot to them. So any droplet will evaporate a little bit and form a small layer of gas between itself and the table. As a result, the drop is very sensitive to weak forces. Here are liquid nitrogen droplets sliding down a plane next to a magnet. Nitrogen is very weakly diamagnetic, so nothing much is going on. The drops are unaffected by the magnet. Now here are the liquid oxygen droplets. They are strongly affected by the magnet. They spiral around it. Oxygen is strongly paramagnetic and the magnet exerts an attracting force on the droplets. Okay, so now we're familiar with two forms of magnetism displayed by materials we wouldn't usually call magnetic: dia and paramagnetism. Both effects are weak and only exist in the presence of a strong external magnetic field. Specifically in this chapter, we learned that some atoms do have a net magnetic moment, as the magnetic moments of some of their electrons do not cancel out. If an external magnetic field is applied to a group of such atoms, it aligns their magnetic moments, producing a very weak attracting field in response. That's paramagnetism. Let's move on to the real magnets. Not all atoms with a net magnetic moment ignore their neighbors. Some are actually very much influenced by their neighbors. One such atom is iron. When you put together a small group of iron atoms, their atomic magnetic moments align and lock up with one another strongly, a phenomenon we only understand through quantum physics. All of their magnetic moments add up in a very powerful way, and a group of atoms produces a net magnetic moment that is many orders of magnitude stronger than what you would find in a paramagnetic material. That's ferromagnetism. And guess how one says iron in Latin? Ferrum. So is that it? Have we explained magnets? Well, that sort of would imply that anything made out of iron is a magnet. And we all know that's not the case. For instance, this screw is made of iron, and yet it clearly does not produce its own magnetic field. To understand that, we need to zoom out one last time and figure out what happens at the scale of groups of atoms. It turns out that iron atoms are a bit snobbish, you could say. They only tend to agree with the neighboring atoms around them, their inner circle if you like. But they completely ignore the other atoms far away from them. So, a block of iron spontaneously divides itself up into many ferromagnetic domains, which are groups of atoms in which the magnetic moments all point in the same direction. Each domain has a net magnetic moment, but from one domain to the next, the orientation of the net moment is random. So, at the scale of the material, the net moment averages out, once again. With a grid of magnetic needles, once the needles stop spinning, we can witness the formation of magnetic domains. If we draw boundaries between them, you can see that even better. But if we place the needles in a strong external magnetic field, they all align, the domains merge. The needles behave just like our iron atoms. And what we just saw actually is how you would make a magnet. Finally, apply an external magnetic field to iron atoms, and the domains aligned in the direction of the external field take over the entire material. The atomic magnetic moments add up everywhere, and the entire material finally acquires a strong net magnetic moment. That's exactly what's happening if we stick a magnet to this iron screw. The screw itself generates a magnetic field. But that magnetic field disappears if we remove the magnet. The screw is kind of a temporary magnet. It's an example of a material displaying soft ferromagnetism. These materials eventually reorient back to a disordered state with many domains when the external field is removed. Other materials display hard ferromagnetism. Their atomic magnetic moments are very hard to reorient. They tend to stay frozen in the ordered state forever. And that's exactly what permanent magnets do. So let's do a final recap. In a permanent magnet, not all magnetic moments associated with the electrons cancel out or average out. So the atoms have a net magnetic moment. These moments all line up with each other within small groups of atoms, called ferromagnetic domains. But from one domain to the next, the magnetic moments are oriented in random directions. So groups of atoms don't typically have a net magnetic moment. The moments of the domains can be forced to reorient all in the same direction by an external magnetic field. When the external field is removed, they stay locked in that direction because the moments are hard to reorient. In the end, we get a strong and stable magnetic moment at the scale of the magnet itself. So, we've come a long way to finally understand how permanent magnets work. But what do they have to do with our particle detector in space? Neodymium magnets, exactly like this one, are at the core of the AMS experiment. They're the strongest permanent magnets available commercially, and a great example of hard ferromagnetic materials, just like we talked about earlier. In the detector, 6,400 of them are assembled into a cylinder of 1 meter in diameter. Here's a model of the cross-section of that cylinder. The interesting thing about this assembly is that the direction of the magnetic moments of the neodymium magnets is made to rotate as we go along the circle. If we bring a grid of magnetic needles, we see that the field basically cancels out outside the circle. There's almost no effect on the needles. But inside the circle, all the needles are oriented in the same way. We have a strong, uniform magnetic field. That's a pretty clever magnet arrangement, which achieves two very important goals at the same time. First, AMS is installed on the International Space Station. We wouldn't want any stray magnetic field extending into space outside the detector. It would be quite inconvenient if the astronauts were magnetically attracted to AMS each time they do a spacewalk, for instance. Second, we want a strong magnetic field inside the detector in order to bend the trajectory of any electrically charged particles that happen to go through AMS. The curvature of the trajectories we detect gives us information about the properties of the particles. And why are there particles going through AMS in the first place? Well, in space, high-energy particles travel from the far reaches of the cosmos in all directions. They do not reach us on the surface of the Earth because we're shielded by our atmosphere. But from its front row seat above the atmosphere, AMS is ideally located to observe these cosmic high-energy particles. By studying these particles, we hope to learn more about the big mysteries of our universe, such as dark matter and antimatter. But that's a story for another day. Thanks for learning with us throughout these adventures into electricity and magnetism, and see you soon in the next video.